Welcome back. Today's topic is digital to analog conversion. As we have seen in the last 2 weeks that digital relays, they do require conversion of analog signals to digital signals. And for this digital signals and to process the digital signals, we are supposed to first convert the analog data which we do have to the digital form and then process it in the digital processing subsystem, and then again convert this digital data into analog data and then send it back to the trip circuits. So the entire process, it requires analog to digital conversion of the data and also digital to analog conversion of the data. In the last week, we have seen different components of the first two subsystems of a digital relay. We have seen the subcomponents of signal conditioning subsystem, and we have also seen the conversion subsystem components also. And in the next week or at the end of this week, we will discuss this subsystem of digital signal processing. But in the entire subsystems, if you carefully see, there is one particular component which converts digital to analog signals and also another component which converts analog to digital signals. So in this class, we will see how actually a digital signal is converted to analog signal. So in the previous lecture, we have gone through this conversion subsystem where we have discussed about sample and hold circuits and also digital multiplexer, and we have realized different types of digital multiplexers. We have realized 2x1, 4x1, 8x1, 16x1 multiplexers using logic gates. And in this video lecture, we will discuss about how digital signals are converted into analog signals. I hope that by the completion of this lecture, you will be able to compare the different DAC which are available or extensively used in digital relays. DAC stands for digital to analog converter. So we will discuss two different types of DACs which are available in the market and extensively used, and then I hope that you will be able to determine the analog output voltage which is corresponding to the given digital input. So let's start with the introduction with the DAC, and then we will discuss the types of DAC, and in particular we will concentrate on how these two DACs do operate. So coming to the introduction of DAC, a DAC, often referred to as a digital to analog converter, it converts a digital signal to analog signal. So this is the block diagram of a DAC where the digital input is processed. So this is DAC, and you will be getting an analog signal as an output. So this digital signal, which is in the form of input, it will be in the form of either 0 or 1. So all the digital signal, it can be 2-bit, 4-bit, 5-bit, 6-bit, any number of bit, n's. But each bit can be either 0 or 1. So these we call them as binary inputs, which is in the form of either 0 or 1. If it is given to a DAC, then you will get an equivalent analog output. So what are the different DACs which are employed in digital relays? The first one is a weighted resistor DAC, which was one of the oldest mechanisms, but nowadays everybody is using R to R ladder digital to analog converter. So let's have a quick look about the operation of these two, and then we will compare the performance of these two DACs. Coming to the first one, the weighted resistor DAC. This weighted resistor DAC, it produces an analog output by taking in the digital binary inputs by using binary weight resistors. So it basically employs binary weight resistors, and it will be an inverting adder circuit that I'll show you the diagram, and we will determine the output voltage which is equivalent to binary digital inputs. In short, this binary weight resistor, since it consists of this binary weight resistors, it is often called as a weight resistor DAC, where every input is basically, every bit is followed by a resistor 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, like that. Every bit, this is MSB, this is LSB. If there are more number of bits, then if it is an n-bit device, then you will be having, so each bit is multiplied by this value. So the higher the number of bits in your digital input, then more number of resistors are required. So let's have a quick look about these things. So this is a 4-bit digital to analog converter arrangement. Now if you carefully see, this is your least significant bit, and this is your this is your least significant bit, and this is your most significant bits. Now let us suppose this is your voltage. We call it as a reference voltage, and here these are the switches. Each switch is having two states. This is 0 and this is 1. 0 and 1. 0 and 1. 0 and 1. Now based upon the, see, now I have considered a 4-bit, which means that I do have S0, S1, S2 and S3. In each bit can be either 0 or 1. So depending upon its two options, I am showing a 0 and 1. If it is 0, this switch will be connected to ground. If it is 1, it will be connected to your reference voltage. Okay, and see, each switch here is now connected to your reference voltage, which means that the possible option here is this is 1, 1, 1 and 1. So in this case, as shown in the figure, the digital input is 1, 1, 1, 1. Now see here, the least significant bit is directly connected to your reference value, whereas as you go to the higher order bits, each higher order bit, as you go stepwise, the resistor is divided by an equivalent of 2. So if it is R by 2, here is R by 2 square, this is R by 2 cube, and if it is an n bit, you will be getting R by 2 power n. So this is a difficult thing. If the number of bits are going to increase, then it is difficult for us to find numerous number of resistors. Different values of resistors are required, and with that much precision, it is difficult for us. So that is one of the biggest problem with this type of DAC, because it requires different values of resistors, and that too with precision. Okay. So apart from this, now once these are being fed, now if you carefully see, this is an op-amp, operational amplifier. So all these inputs are connected to your inverting signal or inverting inputs, whereas the non-inverting input is connected to your ground. Okay. Now in this case, let us suppose this is 1, 1, 1, 1, right? So in this case, you know how op-amp works. Op-amp is basically works on virtual current phenomena, right? So which means that if this is, the potential between these two will be 0. So now this point is at 0 volts, right? So automatically this point also will be at 0 volts. So this is the concept of op-amp. I think you do remember, you might have studied in your AD, right? So now if you carefully see at this particular point, now if you can check, there are how many number of, let us apply KCL at this particular point of, I'll consider it at this one as A. Okay, at point A, how many paths are there? Let us see. inside, if it is virtual ground means no current will be entering into this op-amp. So how many paths are there? Literally there is one path and there is another path. In this path, there are 4 subpaths. This is one subpath. This is another one. This is another one. And this is another one. Right? And all paths, they are dependent upon whether these switches are 1 or 0. Now, there is another path here which it goes to V0. Now, in this case, if I write for this triple one, now I'll take this one as 0 volts, right? So, for the first path, it is 0 minus VR by R. Second path, it is 0 minus VR by R by 2. Next one, 0 minus VR by R by 2 square plus 0 minus VR by R by 2 cube. And this is another path, right? It is 0 minus V0 by 0 minus V0 by RF, forward resistance. Now if you carefully see, this by 2 will go to the up one. So if I take VR as common, so what I'll be getting here? I'll be getting here, if I take VR by R as common, what I'll be getting here? Here it is minus 1, here it is minus 2, here it is minus 4, here it is minus 8. Right? And here I'll V0 by RF. So this is minus 8, minus 4, it is 12, 13, 14, it is 15, right? So V0 is equal to minus 15 RF VR by R. Right. It is just like if you take the values of R and RF as equal. If you take them as equal, then automatically, if RF and R are both are equal, then V0 is equal to minus 15 VR. See, which means that the values of the different options which we do have here is, it can be 0 or it can be minus VR, it can be minus 2 VR, it can be minus 3 VR, it can be minus 4R. So like that up to minus 15 VR options are there. So for 16, for 4-bit means, since it is a 4-bit, you can have 16 different digital inputs, binary inputs. Right? So for each of these, you can have a different voltage which you can set up here. It is 0, 1, 2, 3, 4, 5, 6 up to 50. 0 to 15, which means that you are getting 16 different values of voltage based upon the digital input which you are giving. Okay, see, this is what I have mentioned here. See, the binary input be W3, W2, W1. This is a binary input where any of these will be either 0 or 1. And the logic voltage which represent individual bit are the switches S0 to S3, which we have seen. See, these are the switches S0, S1, S2 and S3. Right? These are the switches. So VR is the reference voltage, and if any of this bit is 1 or 0, if it is 1, the corresponding switch is connected to VR. If it is 0, it will be connected to ground. Okay. So now, see, working. The values of the circuit elements are chosen such that successive resistors on the input side are related in powers of 2. That is what we have seen. 2. The next one will be R by 2. Sorry. The first one is R, the next one is R by 2, the next one is R by 2 square, next is R by 2 cube, and if there are n bits, it will be R by 2 to the power of minus 1. So the individual resistors are inversely proportional to the numerical significance of appropriate binary bits. So the non-inverting input terminal of an op-amp is connected to the ground, and that means 0 volts is applied, which we call it as virtual ground. This is what I have said, which means that between the inverting terminal and the non-inverting terminal, I think you do remember this one, right? Right. Literally speaking, virtual ground means no current enters into the terminals. Okay. And the these 2 points will be having the same voltage. This is what a virtual ground actually means. So if this is connected to ground, then automatically here also you will get 0 volts. So whatever the input which you will be giving here, Vn, this will be 0. So that's why we do generally employ resistor here, R, and this is Rf, and this is, okay. So this is a working. So if this is the case, I think you do remember, since this is 0 volts, you apply KCL here, right? So what you will get? 0 minus V input by R plus 0 minus V output by Rf is equal to 0. So if you solve, what you will get? V0 is equal to minus Rf by R1 into V input, which means that based upon the values of Rf and Ri, you are going to have an amplification of your input voltage, and that too in a negative format. This is what an op-amp does. Okay. So let's not go into the operation of op-amp, which you have already studied. So let's stick on to this one. So I hope that now you have understood how it is going to work. See, I have written governing equations for 4 ones, which I have shown already for you. Right. So this is a simple representation of weight resistor. See, normally what I have taken here R, I have taken R by 2, and I have taken R by 2 square, R by 2 cube. Or otherwise, if you want to take as R, as you go to the least significant bit, you can multiply it with 2, 2, 2, 2, like this. Okay, any of them is okay. Okay, so now I have for corresponding, see here in this case, if the binary input array of 4 bits, this is a problem. The binary input array is given as 4 ones. Determine the corresponding output voltage. The values of all the resistances are 10 kilo ohm, while the reference voltage is minus 5, which we have already seen, right? So we have already seen this thing. What we have obtained in the last one, it was V0 is equal to minus 15 Rf by Ri V in or V reference. This is what we have seen, right? We have done for the same case, right? So what is the value which we will be getting here? Minus 15. Both are same. Rf and Ra both are 10 coulombs, so they will get cancelled. Vr is minus 5. So what I will be getting? I will be getting 75 volts. Right? This is what I have written here. So simple thing, how we are going to solve these type of problems. Okay. And what are the disadvantages? I have already told you that the difference between the resistance values corresponding to least significant bit and most significant bit, it will increase as the number of bits present in the digital input increases. If there are n bits, then you are supposed to select resistors of R, R by 2, R by 4, R by 8, like that up to R by 2 to the power of n minus 1. This is not possible to select this many number of resistors. If you do have n of 12 bit or 16 bit, you cannot have 16 resistors of very precise values. So you do have a difficulty in selection too many number of resistors, and also to have precision. More accurate resistors is also a tough task. Okay, so these are the disadvantages of weighted resistor digital to analog converter. Okay, I hope you have understood this one, and in the next video I will discuss about this R to R ladder type of digital to analog converter.